Hello. In this presentation for the Chicago Predictive Policing, we're going to be covering the exploratory data analysis process and the feature engineering steps used to prepare the data set for predictive modeling. The goal of exploratory data analysis is to uncover structure and relationships in the data. EDA helps identify patterns, anomalies, and correlations that guide how we build and evaluate our model. This stage transforms raw data into actionable insights. The statistical overview of the data. In the training set, we observed an average of 370 crimes per day and an arrest rate of about 12%. The data set's latitude and longitude range covers the full extent of Chicago's geography, ensuring good geo coverage. The daily distribution of crime counts was slightly right skewed, meaning that while most days have average crime levels, a few days experience exceptionally high activity. Recognizing that skew helps us to decide when to normalize or log transform features for modeling. Crime trends over time. When we look at crimes by month, over several years, a clear pattern emerges. Crime levels have gradually declined, but within each year, there's a strong seasonal cycle, peaking in the summer and dipping in winter. This consistent pattern validates the inclusion of features like month and season in our predictive model. Crimes by type. Categorically, theft and battery dominate the data, representing over half of all reported crimes. Other common categories include criminal damage, assault, and robbery. The imbalance is important. Without adjusting class weights, predictive models could become biased towards these majority classes. Visualizations through the bar chart helps to clearly show these proportional differences. Spatial hotspots. Mapping crime spatially reveals dense clusters in the Loop, Austin, and Inglewood neighborhoods. Using latitude and longitude grids, I calculated a spatial density threshold. The top 10% of cells were marked as hotspots. The new hotspot feature lets the model distinguish between routine and high-risk areas. The features engineering overview. Features engineering enhances the predictive power of our data set. I created 4 main feature types: time-based, hour, day of the week, month, season, and weekend flags. Spatial, hotspot indicator from latitude, longitude densities. Temporal, time, lag features capturing 1 to 7 day history of total and district level crimes. And contextual, arrest flags with optional weather variables like temperature and precipitation. Engineered features. Here's a snapshot of the newly derived features. For instance, all 5 sample records occurred at 11 p.m. on Friday in December. Hour equals 23, day a week is 4, month is 12, season equals 1, winter, and this weekend equals 0. The hotspot flag equals 0, indicating that these incidents occurred outside the highest density zones. This confirms the success of our time and spatial creation logic. Business interoperability. Each engineered feature connects directly to real-world decision-making. The hotspot indicator guides patrol deployment. Hour and day helps schedule officers efficiently. Lag feature detects short-term escalation in crimes, and weather variables anticipate risk under extreme conditions. This alignment ensures our features are both statistically valuable and operationally useful. Key takeaways. In summary, the exploratory analysis revealed strong space and time trends in Chicago's crime data. We cleaned the data set, identified correlations, and created interpretable features to capture time, space, and context. PCA simplified the data set while preserving meaning, leaving us ready for predictive modeling in the next phase.